Yeah, so good afternoon, and then I would like to first start to thank Satyaprada and Brijesh for inviting me. So this is something which we recently theoretically predicted and motivated the experimentalists to validate our thing. So it is not the other way. So we first predicted, and then I was talking to my experimental collaborator to synthesize this, and then they confirmed the ferromagnetism as well as the orbital ordering here. So this is like it's not something new, but this is a old wine in a new bottle. So this cesium MnF4 is a very well-known perovskite, fluorine-based instead of oxide. So this is something which we recently did, and I would like to share some of the interesting results which we had. So first I will start with some introduction, and then magnetism in perovskites, which is well-known, and coming to this history of these layered perovskites, especially with the fluorine, and then the gap areas and predictions from theory, and how we motivated the experimentalists to validate our prediction, and then we like to summarize. Yeah, so this is something which is not very new, and this first thing started in 1950s. So where they tried to report this K2NiF4, which is having a similar to perovskite structure but with tetragonal lattice, and then it is broadly belonging to this Rudolphs and Popper family of layered perovskites, and then came this quaternary or even more like yttrium, barium, copper, iron, oxygen 5, and then came this popular lanthanum manganate, where we have several structural distortion, where there is whole dope thing relates to the ferromagnetism and so on. And then there is also this AMnF4, where we have this alkali metal like potassium, rubidium, cesium, and then they consist of distorted octahedral layers. And then when you try to have with this potassium and rubidium, so they are likely to be antiferromagnetic in nature. But the cesium, which is only exception, which is a ferromagnetic insulator or semiconductors, that was reported in the literature. So now there is, as we talk about this particular transition metal oxides, so this orbital ordering is one of the famous, popularly known phenomena, which depends upon how the d orbitals are actually occupied with the T2G and EG, and then eventually it will lead to several kind of distortion. So from prototype is orthorhombic system, where we have a distortion, and this will lead to interesting orbital physics, and then we do see orbital ordering, and then which can coexistence with this magnetism, and then there is a elongation or compression depending upon this Jahn-Teller effect, and then this is so popular in manganese system. Here manganese is in 3+, which is highly Jahn-Teller active. So now let us start with the experimental literature, which is already reported for this early alkali metal manganese with fluorine. So there are crystal structure details with X-ray as well as from the neutron data, and then they try to confirm the antiferromagnetic nature, and then there is a theoretical work by Kanchana and co-workers from IIT Hyderabad, where they tried to propose orbital ordering as well as a quasi two-dimensional magnetism in potassium and rubidium based thing. This is purely from the first principles. So this is what regarding this potassium and rubidium. And then cesium is much more interesting in the sense. So there were several controversy which is already available in the literature regarding the space group of the system. Of course, the system is reported to have a tetragonal symmetry, but then each experimentalist tried to contradict with the other experimental group. No, you are wrong, like that. And then interestingly, there were some high pressure studies in which people tried to see a high spin to low spin kind of transition, which is also reported experimentally, and this may lead to some kind of structural transformation, which can also destroy the magnetism associated with the lattice. So this was the thing, and then there were some controversy, as I mentioned, about the basic crystal structure and the associated space group. So that was the starting point for us, and then we want to address this from first principles theory. So how we can try to confirm the real ground state structure, and then rather than predicting, we also want some of the experimentalists to validate our prediction through X-rays and neutrons. So that is what I will be showing now. Yeah, so when we try to discuss about this potassium manganese fluorine 3 and rubidium manganese fluorine 3, which are well known to be antiferromagnet, and then when it comes to the cesium MnF4, there are two kinds of prototype space groups which are reported. Both reported that system is found to be ferromagnetic, and then they still have a debate which one is the real ground state, and then if it has to be a ferromagnetic insulator, what is the kind of orbital ordering it should have. Okay, how it can stabilize in a ferromagnetic state? That is a basic question which motivated us to start this particular problem. And they also, as I told, that around 35 plus GPa, they do see high spin to low spin transition, which is purely driven by pressure. And then this is also associated with the structural change from the well-known tetragonal symmetry. So these are our starting point. Yeah. So then we try to look into the group theory into much deeper extent and then try to see the glacier notations. So this P4 bar NMM symmetry, if you consider, so then it will be more a ferrodistortive orbital ordering of the compressed octahedra as it is supported by this P4 bar NMM. So this is the prototype thing which belong to the particular space group. But whereas if you try to see this P4 bar N, if you assume this particular space group, both of them have a tetragonal prototypes. And then in this particular thing, we do see antiferrodistortive ordering because of the elongation of the octahedra, which is supporting this particular space group. So now, how to comment on this? Because these both the systems are available and both the space groups are reported, and how we can try to confirm the ground state of the system and the associated magnetic properties. So that is what we started, and then whenever there is a controversy, we always do an unbiased way of screening, and then we start with the prototype structure and try to see the lattice dynamics, and through phonons we try to address the ground state structure. That's what we are doing here. Yeah, so especially for the young students, when I started my PhD, so Professor K.P.N. Murthy, who is no more, he suggested me this particular paper by G. Venkatraman, which was published in 1978 in Bulletin of Material Science in the Indian Academy. So this is a very good paper to read for the students, especially how one can try to relate the soft mode with the structural phase transformation, which is purely temperature driven. Okay, so and then this is purely a distortive phase transformation where we go from one particular structure to other structure. It can be driven by pressure or temperature, any of the thermodynamic parameters, but then clearly it shows that how we can try to understand this particular structural phase transformation through phonon modes or the soft modes. So that is what the interesting paper, and then subsequently this was the first paper which was published in 1979 from Reactor Research Center Kalpakkam. Professor Sushanta Dattagupta might be aware of this particular thing by Professor G. Venkatraman. And then subsequently there was another paper in 2012 which is extension of what Professor Venkatraman published in those days, and then they also tried to the same title, of course. So this was published by Oxford Group, and then these two papers for students especially they should read if you are trying to understand the structural phase transformation in solids. Yeah, so then there is an interesting thing. So we always try to understand the electronic structure and also the phonons. So the moment for the students, especially when you try to see some soft mode or the imaginary phonon modes in the solids, what is the significance of that? Okay, can we rule out that, okay, the structure is not of use, or how we are going to proceed further? So whenever this is a classic example of this tin sulfide with the CMCM orthorhombic symmetry, in which when you do phonon calculations within the harmonic approximation, you do see two kind of imaginary phonon modes. One is at the gamma point and the y point. And then eventually, okay, there is some interesting physics which is hidden in this thing, and then one can try to freeze that particular phonon modes and eventually try to get the information about the structural transformation associated with this. And this is particularly interesting in case of ferroelectrics, where we have a high symmetry, non-polar to a polar transformation, which is purely driven by temperature. And then by using this harmonic approximation, which is not so good, which has to be taken with a pinch of salt, but still we can try to address some of the experimentally observed transformation, which I did with Surajit Saha from ISAR Bhopal for some of the perovskites. So here when you try to freeze these particular phonon frequencies which are imaginary, then we do get a nice double well like thing, and then eventually you can get another space group, so which is purely a displacive transformation from solid to solid, from one particular space group to other particular space group. So this is one of the approach which we followed and tried to see that, okay, let me try to shed some light on the real space group of the system. So and then we tried to And then of course one has to, because we are within the harmonic limit, this has to be taken with a pinch of salt, and then we have to make sure that we have included all the correlation effects, the spin orbit. I don't know whether it is not working. Maybe I am loud enough, probably. Yeah, please check. Yeah, so that is the caution which the younger students should take care. Yeah, so then we started unbiased search. So assume that there are no experiments, but I have idea that this belongs to a tetragonal symmetry. Fine. So we started with the P4 bar MMM symmetry, and then of course, since this is a magnetic system, we use the correlation effects, the Hubbard U, to localize the manganese D states and try to compute the structural aspects, and then this experiment corresponds to unbiased thing, not belong to this particular cesium MnA4. We started with the prototype thing, and then we tried to optimize. Then, so we computed the phonons. So, and then surprisingly, so we got to a large imaginary phonon mode at the M point as well as at the A point. So this is with this particular space group P4 bar MMM, which is 123. Oh, I am not comfortable in standing.
Okay. Actually, we don't have bed.
Yeah, the problem nahi hai. Okay, so this is what we got it, and then we could see huge imaginary phonon modes. One is at the M point, another one is at the A point. So then these are the corresponding animations of the vibrations of the phonon in the particular mode, and then we try to see that, okay, so this mode, especially the M point and the A point, they are more of Jahn-Teller active. Okay, so they are trying to distort that particular lattice, and then we do see a Jahn-Teller kind of distortion, which is purely driven by the M mode and the A mode in the Brillouin zone. So then with this as a starting point, we try to get the possible group subgroup transformation, okay, and then we try to get all the glacier notations associated with that, and then we try to screen all these possible space groups which are related to this particular space group by freezing the phonon modes at the 2 points which I showed, and then we could see that this P4 bar MMM corresponds to 0, and then we have P4 bar N structure which is more negative when compared to all these things, and then we try to see that, okay, what will be the stability of this particular P4 bar N structure. So, and then this is the energy gain from the structural distortion. We tried to move the atoms and try to compute the energy and try to plot this, and then these modes, as I suggested, they are Jahn-Teller active, and then we do get a double well like future when you try to do this A and M, but whereas in X and Y it is not very significant or prominent. Yeah, so then we identified that, okay, now the P4 bar NMM which were proposed by the experiment is not the real ground state, and now when we try to consider this P4 bar N, which is also a tetragonal with this kind of glacier notation, and then this is a particular ground state where we do see all the phonons are well behaved and we don't have any imaginary phonon modes, and then this is our conclusion point, and then we say that as suggested by this experimentalist Mn3+, then we also have a Jahn-Teller active with this particular structure at the M and X point, and then this collectively tried to conclude as this particular P4 bar N is the ground state. Fine. So now what else? How about the magnetism? So then we all know that, of course, we tried to play with different magnetic configurations, and then we concluded that the total energy is more favored for a ferromagnetic ground state. That is fine, and then we took the standard traditional Heisenberg exchange interaction and then tried to compute the Curie temperature, which is not so great because Heisenberg model is well known to overshoot the thing, and then we got around 22.2 Kelvin, which confirms it's a weak ferromagnet. The Curie temperature is not very strong here, so that is our conclusion. And then as a next step, we also try to understand the electronic structure because this is a semiconducting system, and then we do get the gap both in the spin up and spin down channel. And then interestingly, so we also see a nodal cage kind of behavior in the states which are close to the just below the Fermi level, although it's not interesting because the system is gapped actually. So, and then the total magnetic moment is around 4 Bohr magneton, which is quite good with the experiments, and then there's a possibility of nodal line like dispersion from the electronic band structure. So, and then comes what makes it to be ferromagnet. So most of the oxides or the fluorides, they prefer to have antiferromatic ground state, But whereas this particular system, we can see that, so when you try to plot the orbitals, we do an antiferrodistortive, like it is in this plane and then the next manganese in this opposite plane. So we have a manganese-manganese separationer, like which is around 4 Armstrongs, as DD always says that in double perovskites. The chromium, iron separation is around 7 Armstrongs, and then the molybdenum sits in between the two iron, they try to mediate the coupling. Here also the fluorine is the key player. So the manganese distance is around 4 Armstrong, and then the fluorine is sitting in between and trying to mediate the this is similar to the kinetic energy driven which you always propose for double perovskites, but this is fluorides in the case of oxides you propose. So this follows a similar thing, and this EG orbital which is having single empty place facilitates antiferro-orbital ordering. Because of this, the system is becoming ferromagnet. Otherwise, it would have become an antiferromagnet. That's what we concluded. So now this is our conclusion. Then as a next step, since we also did phonons, we want to compute the spin-phonon coupling. Okay, and then try to see what will be the order of the magnitude of the spin-phonon coupling. So, and then we could see that the AG-Raman modes, EG and AG, especially these BG modes, give relatively large spin-phonon coupling. So don't see the magnitude is 1.96, but this is relatively large in the context of spin-phonon coupling. And then we do see that this system could be a potential spin-phonon coupling based system also. So I hope Surajit Saha will be validating our predictions from ISR Bhopal. Yeah, so now so far we have done only the prediction. Then I talked to my experimental collaborator. So Professor Brendan Kennedy from University of Sydney, who is a solid state chemist like Professor Ganguly. So, and he was kind enough to agree to our suggestion, and then he started preparing this sample, although people say cesium is very toxic. And also they have to do some hydration like that, although I am not a chemist in preparation, but I heard from him. So, and then he could try to prepare the polycrystalline sample, and then they are trying to fit these two models which was proposed, P4 bar NMM as well as P4 bar N model. And then he took synchrotron X-ray diffraction as well as temperature dependent neutron diffraction in Australia, and then they could confirm that the P4 bar N model tetragonal which we proposed from the theoretical calculations, it is exactly matching with the experimental X-ray as well as the neutron diffraction. So that's what they say, and then they confirm the presence of the Jahn-Teller distortion, which is a mandate for this particular system in the P4 bar N crystal structure. Yeah, so it is a weak ferromagnet. So the hysteresis, these are the experimental measurements which is done by them, and then maybe as a function of field this can be improved. I don't know much about this thing, but they confirmed that the ferromagnetic ground state of this system. Yeah, so I would like to conclude that. So we perform this unbiased calculations through phonons, and then try to confirm the ground state of this particular system, and then we try to say that this, instead of P4 bar NMM, the system prefers to have this P4 bar N space group, which is also tetragonal, which was first predicted by theory and confirmed by experiment. And then this magnetization measurement show magnetic transition at 20 Kelvin, and this the magnetic moment which is observed from the neutron is 3.76, whereas our theory is slightly tending to overestimate the moment. And then we confirm a strong in-plane exchange interaction and weak interlayer coupling from this thing, which confirms the quasi two-dimensional nature of the system. Yeah, this paper recently appeared in Physical Review B, and then this two students from IIT Hyderabad and University of Sydney, they tried to be the main key players, and then we had Brendan Kennedy for the synthesis and Camilo from Santander for helping us with the phonon things, and then of course we did this work with collaboration with Kanchana. Yeah, so I would like to, most of the calculations were done in Paramrudra cluster in IUSC New Delhi, and then the students were supported by Inspire and University of Hyderabad, and then this Australian synchrotron thing for the neutron measurements. Yeah, thank you very much. Yeah, maybe you can have this.
So yeah, thanks for the nice presentation. We should be having a lot of questions.
Yeah, yes.
So in this structure there are two manganese sites.
Yes.
And one have 3 Mn3 plus, one has...
No, Mn3 plus alone.
Or alone.
Yes.
But both the sites...
There is no charge ordering like
There
that.
is no
No.
Okay.
Yeah, it's a ferromagnet.
The magnetization results, it is not typical of ferromagnet.
Yes, it's very weak.
It looks like more, weak ferromagnet is an antiferromagnet typically. But do you have neutron diffraction that in the ordered state?
Yeah, so I have the pic, maybe I can show you more details.
Yeah.
Yes, but from the calculations, we do see that the ferromagnetic state have more minimum energy, the ground state.
Yeah, I want to see the experiment.
Yeah, definitely, I will show that.
Hi, Becky. Very nice talk.
Yeah, thank you, Debbie.
Before N structure, your all negative phonons has gone.
P4 by N, we don't see any.
You do not
Yes.
see any negative phonon.
Yeah, that is the fingerprint which we tried to see that. Okay, this structure is quite stable.
Yeah.
And
Because you have not shown that phonons before N, have you?
No, P4 by N is stable. I showed that.
So, okay. And the next thing is that you have shown some TC calculation.
Yes.
Is it mean field?
Yeah, of course. That is not, we have to do a rigorous Monte Carlo. No. This is mainly based on this Heisenberg standard, which is a rough thing.
And then lambda parameter you calculated by taking as a mean field approximation
Yes.
within harmonic approximation.
Yes, of course.
So,
Everything is within the harmonic limit.
yeah. So you are dividing by that
Yes.
saturation magnetization.
Same, yes. But there's a difference between the theory and experiment. It's always there.
Yeah.
So,
But experiment, has it shown any spin phonon coupling for these systems?
spin phonon coupling experiment they have not done yet.
Oh.
This is the pure theory.
Oh.
Swaraj has to do Raman.
Yeah.
Yeah.
So, any more questions?
Yeah, somebody, student. Yeah.
This is a nice talk.
Thank you.
Is any practical use of quasi two-dimensional ferromagnetic things?
Practical use.
Yes.
Yeah, first of all, the physics is interesting. Why it is quasi 2D? That is my question.
Okay.
So I am a theoretician, so I am first trying to understand what makes the system to be ferromagnet. That itself is important. After that, we'll go for practical application. That's what the answer.
Any more questions, especially from the students? No? Okay, let us thank the
Yeah.
speaker again.
Thank you.